Mr. Daniel Raravi. Mr. Daniel is a Marketing and Strategic Initiatives Director at Mastercam. With an engineering background, Mr. Daniel is tool and die alumnus from the government and engineering background. Mr. Daniel he did PG in international business from Symbiosis. He has professional experience of more than 2 decades. Before it, he was associated with Delcam for a decade. On behalf of Delcam, he also served as subject matter expert on SME committee at the National Centre for Aerospace Innovation and Research. He is now associated with UAY project for Additive-Subtractive manufacturing research at IIT Bombay. Mr. Daniel has also presented papers at national and international seminars on various topics relevant to machining and manufacturing. Today, Mr. Daniel will share his insights on CAM for advanced manufacturing.
My name is Daniel Raravi, and I look after market strategic initiatives for Mastercam India. And my topic for today is focused largely on CAM for advanced manufacturing. Before we go into the details of what I'll be speaking today, I thought I'll have a small perspective on what advanced manufacturing is. My focus largely will be on discrete manufacturing, with a focus on how this advanced manufacturing within discrete manufacturing has progressed in the past decade or so, and where it is moving ahead as well. But before we do that, let us spend a minute or two in defining what this manufacturing is in this purview. Well, manufacturing has been happening across for the past 100 odd years, and more than 100 years, actually 20 years, when we look at the first industrial revolution to the current industrial revolution 5.0. And within this, there have been numerous technologies that we've been using to make things better, in short. What has happened in the recent past is we've been able to manage the simplification or the easy access to information, to computing power using information technology, and then applying engineering practices or manufacturing practices within this domain in order to reap benefits such as greater precision or accuracy in manufacturing processes, to have better quality products, to get faster production times, to make utilization of resources and materials. And finally, of recent, where we are trying to minimizing the impact of manufacturing on the overall detrimental effects it has on the environment. So advanced manufacturing looks at, using technology, information in order to give this benefits. The examples of advanced manufacturing technologies would be, discrete CNC machining, which is our topic for today, additive and hybrid manufacturing using 3D printing, and a combination of subtractive and additive manufacturing practices. Then there's advanced robotics. This is essentially using industrial robots for purposes of manufacturing related to other aspects, for example, tape laying, for example, or milling, adhesive laying, a number of such technologies. Also, this topic looks at the digital twin, or having they call it cyber twin, a virtual existence, a virtual model of a physical asset. And with newer horizon technologies, the use of artificial intelligence and machine learning in order to improve and further refine these processes to help in knowledge-based manufacturing, essentially. The industries that are a derivative of these, industries that benefit from these processes would be largely the aerospace, automotive, electronic, and medical devices industry. This list is not limited, but then primarily these industries derive larger benefit currently. But one of the aspects of CAM in current perspective is high-speed machining, and this is one of the components of advanced manufacturing. High-speed machining involves various strategies, whether it is in turning, which is the basic of CNC machining when we look at it, 2.5D milling and 2D turning, some of the examples of basic CNC machining. And within this, we have two technologies that I would like to largely speak about today. One is high-speed machining in 2D turning by the use of dynamic turning. So let's take a look at this video. Typical 2D turning process is where you have cutting tools which are either left-handed or right-handed, and then you use them to cut in unidirectional. They are unidirectional tools, which means that you can cut them only in one direction. But of late, advancements within CAM technology, especially the strategies, allow for the use of innovative tools such as what you see round insert, which allows cutting from both sides. The advantages of this strategy and tooling is that it allows you to nearly reduce your machining time by 50%. If something would take 2 minutes, you would finish that in 1 minute now, considering that you're cutting on both sides. Of course, the toolpath strategy is also unconventional, which means that there's a lot of research that goes into it in order to create those innovative toolpaths that does not follow a traditional kind of a toolpath. Another innovation is something called as prime turning. Let's look at that here. Not just limited by the kind of cutting tools in terms of geometry. What we saw previously was a rounded insert, but here this is a new prime turning cutting tool which has type A and type B inserts that allow you to do roughing and finishing operation using the same insert. So not only does it help you save machining costs in terms of time, but it also helps you save costs on the inserts as well. You don't need to use many different shaped or many different quality of inserts for roughing and finishing. A similar example we see in milling as well. This particular video I'll also play demonstrates the kind of benefits that advanced manufacturing derives out of toolpath strategies alone. The left side, this specific video looks at a traditional classic toolpath which uses offsetting the shape of the material that we are trying to cut. Whereas on the right side, we see a very a new dynamic strategy that does not really look at the end geometry of the part, but rather looks at the fastest method of cutting any given block of material. And the results are apparent and they're right in front of us. There's a tool breakage here because we tried to run this tool with a specific depth at a certain feed rate, which was probably half of what we are seeing on the right side, which is the high-speed machining toolpath. During the third attempt, we see that it is making some progress. But then initially, as the geometry of the part comes into play, we see a reduction of the feed rate due to a variety of factors. A, that the engagement angle of the tool is high, and the machine tool has intelligent features built in within it called block looker functionalities that reduce the feed rate when it senses a heavy load on the machine spindle. If you look at the right side, we see that there's barely any reduction. We see that the tool is moving as rapidly as it began, and the part is nearly complete in terms of its geometry. The reason why this is happening is because the strategy that is being used here looks at a very controlled engagement angle of the cutting tool in terms of having anywhere between 5 to 8% of the tool diameter as the engagement into the material, whereas it is going many times faster in compared to traditional strategies. Interestingly enough, we see that the total machining time to complete this is 3 minutes 59 seconds, whereas this one was over 14 minutes. Yeah, and the strategy is the main difference in terms of achieving these benefits here. Further, as complexities in parts increase, what machinists or what machining organizations or machining shop floors are trying to do is to try and complete any given part in as less a number of setup as possible. And ideally, this would mean that then need to move such a part into either a multi-axis machine, which is a 5-axis machine, or a multitasking machine, where you would use a combination of milling, turning strategies in order to achieve your end goal of machining. I have two examples here that demonstrate both. So one is where we're looking at cutting a complex, part. This is Darth Vader from Star Wars, in case there are any Star Wars fans here. You'll see that it's a complex piece of part, and the way it's machined from a solid block demonstrates the capabilities of not just the software, but also the CNC tool, the cutting tools that are involved there, as well as the work holding devices. So let's take a look at this video first. Advanced manufacturing strategies that allow complex machines such as the one that we are seeing here, and allowing for using different geometry tools. You get tools that are simple polymers in nature. You have the toroidal cutters, you have conical tip cutters, you have circle segment tooling, other specialist tools, and the ability to use all of these complex machines such as these is what sets apart modern Delcam software, which is also what we could achieve yesterday. Right from the finishing aspects of this part up to the detail in terms of how they integrate the files on the face are machined using very small and thin cutters. You'll see that the diameter of this tool is very small in comparison to the size of the overall cup. These are some strategies here which allow you to make complete use of the strengths of the kinematics of the machine in terms of whether it's a head-head machine, table machine, or whether it's a head and table combination machine, and delivering finish as well as So typically what I was trying to say here is the strategies are designed in such a way such as to benefit from the kinematics of the machine. So whether it's a complex head type where all the moments of the 5-axis machines are on the head, or whether it's on the table type such as what we saw here in this video, or whether it's a combination of head and toolpath strategies, the way in which we are able to use very small tools to bring out the detailing in corners such as these is what sets apart modern advanced CAM softwares in comparison to what they were earlier in yesteryears. Moving aside, let's take a look at another example here. So this is also an example of how not just the typical CAD model with solids and surfaces, but this is an example of how this is something that was done in Noida last, and you will see that the input material is not typical. You would generally work with solids and surfaces. In this case, the model that you see here is made of triangles, as we call it. It's called a polygon mesh in technical terms. So it's a polygon mesh model which was used to generate tool paths, and the kind of surface finish and the quality of the output possible because of new age machines, new age CNC controllers, as well as the strategies that allow you to have a reference within the CAD model. It can be a line, it can be a surface, and then using the exterior of the polygon mesh model to complete the features. Again, a quality of CAM for advanced manufacturing. Then we move to the capabilities of robotic manufacturing. Now, a number of people here may not consider robots for something such as milling, but when you take a look at this example here, so for body styling in automotive industries, there's a clay modeling process that happens. Typically, designers use blades and traditional tools to shape a new model. Aesthetics, especially designers of such automobiles, use traditional tools. But with the help of industrial robots and changing the end tooling to a spindle with a tooling mounted on it, we are able to then generate and model out the parts within CAD software using surface modeling tools, and then providing the output to CNC controls that is integrated with the parts in order to achieve what we are seeing here now. Similarly, for sheet metals, when it comes to trimming and when it comes to making holes with laser tools, robots are again used to give the same results. And again, there are a number of complexities when you're working with robots because of a typical robot has 6 axes, and then something called as singularity in robots, where the robot gets locked into a specific position because it finds either a infinite number of moves or no moves at all when it reaches a specific position. And using advanced CAM software allows you to then program it in such a way that you want that. And typically robots are taught, which means that a process using robots take 24 hours. It means that to teach a robot how to do that process would take an equal amount of hours or more, if not. But of modern CAM software for robotic manufacturing, you're able to do it in a matter of a few minutes to a few hours, and that's the strength of this. Then we come into the adaptive machine or additive manufacturing side of things, where CAM is heavily involved, not just in the manufacturing bit, but also in the modeling bit. Here is an example of a direct deposition method using laser. The part is being built without any substructures or without any support structures. This is because the 5-axis machine is orienting in such a way that the deposition is happening perpendicular to the angle of deposition here. So a new part can be produced. This is an example of what is being done currently. This is something that we are doing in IIT Bombay. This was done last year. And finally, the similar technology is used for adaptive manufacturing. What is adaptive manufacturing? When we look at this impeller here, it's got some damages on the leading edge here and on the top edges. Now, replacement of this part is more expensive. But in case we had an alternative to repair only the edges that are damaged, it would on various factors. A, the carbon footprint that is left behind when you create any aerospace part, of whether they're titanium or any of the heat resistant superalloys. If you compare costs of that versus repairing locally damaged regions in situ on the CNC machine, the contrast is far appreciable. And therefore, adaptive manufacturing makes use of advanced CAM systems, both CAD and CAM systems, using also vision-based and laser-based metrology systems to identify where the damaged edges are, and then locally repair it so that you're depositing material only in the areas which are damaged, and then using a combination of hybrid manufacturing, which is using additive and additive-subtractive manufacturing to then machine those areas specifically to blend with the geometry of the overall CAD model. Finally, in conclusion, CAM for advanced manufacturing gives major benefits. One is improved efficiency in the overall manufacturing process. We find a better accuracy and reach in terms of parts that you could not do earlier versus what you can do now, such as the adaptive example that we saw. Enhanced consistency in quality. This can be, this is largely due to the combination of various factors that I mentioned, again, using metrology in combination with additive or subtractive manufacturing to make sure that any part that comes out of the machine perfectly well. And a net result of all of this is reduced costs, wastage, and timelines overall in the manufacturing process. Thank you. And I think that's what I really wanted to speak about today.